Якщо ти хочеш публікувати щось нормально, виважене, щось правильне, а перед тобою є 20 людей, ти стаєш публікувати висновки, це теж знаєте, що це всегда.
LvCS, are we ready? Okay. Welcome back. Please take your seats. Let me know if you can hear me. If this thing's... Does it work?
Can you turn it up a little bit? A little bit louder would be nice.
Could you make it louder? I can do that?
Oh, just keep talking.
Okay. Right. Alright, now I can hear myself. Good. So, how was the first day? Did you see the game? I know you have some plans on that.
Yes.
Good.
Didn't predict the result this score.
Yeah, I think machine learning would fail on that too. Alright. So, yesterday we had the first lecture, first meeting on machine learning class here. And I got some feedback. The feedback was like, it was easy and fun. Today, I'm going to destroy this reputation to the ground. That's right. If you notice something like this, so if you feel like things going this way, let me know. In case you feel that something is missing, is missed, right? Ask a question. You may interrupt me in any time. Ask for details if you're not sure how to move from this one to this one. And also, if you feel that you have enough of it, at least for a while, ask for a break. That's fine. We can make short breaks, and if you feel it's a good time for the break, let me know. That's, I think, because if one of you have this feeling, then others might have it too. So you just help others if you ask for it. I've seen questions.
Sorry, can you share the presentation, please? We will do right now.
LvCS will take care about it. LvCS, when can you make it? Can we go on, or I?
Just proceed. They will have it in.
Good. So, yesterday we started with the linear regression, which is simple and familiar to most of you, because I know that most of you have at least some experience with machine learning. And yesterday we ended up with the idea that we can take gradient from the cost function and use it for gradient descent, basically. The good question might be, why on earth would you do that if you have packages and libraries which do that basically for you? You can do linear regression in R. I'm pretty sure you are familiar with that. I know that some of the lectures did show you or will show you the examples. So the good question is, why would someone implement this from scratch? Why not just using the libraries? And the answer is for some problems you might want to modify the cost function, while libraries support you with some standard ones. So if there is a cost function that fits your function better than the other, then you might want to use some different cost function. Thanks. Sometimes this idea of a different cost function comes from the problem itself, such as, for example, Kaggle competitions. Did some of you participate in Kaggle? Few, okay. Kaggle is a site that offers you a competition in data analytics, mostly machine learning, stuff like that. They give you a data set, you make a model out of this data, and they evaluate it against other participants. The person who come up with the best model gets a prize. The prize might be some money, as well as some job offers and anything basically. So, Kaggle often uses custom cost function. If you want to optimize your model to this custom cost function, that's the one thing you might want to do. The other is that cost function is not given you by God willing, and we'll talk about that a bit later. But first of all, let's take a look at the situation when you might want to modify cost function just because it comes from typical reason, from understanding of the world around. So the model which requires modification of a cost function is called weighted linear regression. With typical linear regression, we mentioned that you might want to add some features. Standard type of features, if you recall the example of housing prices, was just the space, the amount of square meters. And you can make a model which gives you the price of the house given the space of the house. But you also might want to add some more features which increase the variability of the model. For example, it might be adding some information about the world around, such as adding the number of bedrooms, but it also might be adding some combining features, like adding squares. For example, if you have just the space of your house, you can do a model like this one, which is simply linear. But you also might add x squared as an additional feature, which now results in this one. And this will give you a parabolic form of your curve. You can go on with this, and eventually you will end up with a model that fits perfectly all your points. But it goes completely crazy between the points, which is basically what you care about. You don't care about fitting the training examples. You care about predicting the future examples, which are unseen so far. So you might end up with this like this model, which is good from the first. We first look at it because it fits all the points, but it's bad because it doesn't generalize. It just overfit. We call the situation overfitting. There are different approaches to fight overfitting, and fighting overfitting was and will be the most typical problem that you will meet in the field. But there is one approach, at least the linear regression, that offers a beautiful solution to this problem. What's the idea of the weighted linear regression? If you imagine you have a data looks like this. This might be, for example, spending on some online game, which is Y, and the age of a player, which is X. So we expect for some very young people to spend few because they don't have much. Then the person gets some earning, and the person is still engaged in this game, so she spends more. But then this person gets older and older, and different. This person gets something better to do with his life than just playing the game, so she ends up spending less again. So that's just a pattern which you might meet in, say, some casino, online casino, or maybe some World of Warcraft, something like that. So if you like to predict the spending on the game given the age of the player, you might use linear regression, which is a natural thing to do. So with linear regression, you will see models such as this one. See, those points are compensated by these points. They are on different side of the line, and these, there are relatively few. They are compensated by these because they are just more of them, at least according to the idea. But if you care about the prediction for this x1, this model doesn't do a very good job for you, because according to this model, this will be like this, which is clearly far away from those who are similar to x1. So the idea of the weighted linear regression is the following: if we are interested in the spending on online game of this x1 person, which might be, say, 20 years old, we don't really care how good the model is for 40 years old. We care about the accuracy for, well, 20 something or up to 20 in age, right? So if the model fits well for the people of 40 plus years old but fits poorly for the 20 years old, that's the bad model for us, and vice versa. So the idea is the following: we just want to somehow weight the cost function so that the optimization algorithm takes into account those points which are close to x1, and well, the further away from x1, the less the algorithm should care about it. So the idea is like the following: first, we need to modify the cost function, right? Because standard cost function takes into account all points equally. Now we would like to change it in order to weight the points differently according to how close they are to a given point. And this way we can introduce some additional coefficient, which is w, which is omega, sorry. Omega, what's the right pronunciation? Correct me if you know the right one. What's the right one? Omega, right. So, we can introduce the coefficient omega, which defines how important this point is for us. Other things remains the same, it's just this square function. Now we can somehow identify those coefficients. There are different ways to identify those. The most standard is to use this sort of Gaussian kernel. This Gaussian kernel has a bell shape. It's like the following. So this would be the omega with the mean of x, just x, which is x1 basically, but we don't have the normalization term there, so the maximum value will be 1. Basically, if the point xi, which is the training example, is close to x, then we care a lot about accuracy at this point. But the further it from the x, the less important for us the point is. So, now the algorithm is changed. First we should identify for which specific point we would like to make the prediction. So first we identify this x. This way, for the data points we have, we start asking the users, okay, tell me what's the space of the house that you care about, say this is x. Then we use this x to calculate weights for each of those points, for each of the points from the training set. Now we assign some omega for each of those points. And so on. Naturally, for those points which are close to x, for these, omega will be relatively high. And for these, omega will be close to 0. So the optimization algorithm doesn't care much about those points. And then we do optimization, which is a favorite thing to do in machine learning. We like optimizing things. But now we optimize modified cost functions. And then we use the data that we learned after this minimization to predict the price of our house.
Excuse me, can I have,
Sure.
what is tau in this expression for calculating?
Right, that's a very good question. tau defines how wide this bell is. So the bell might be this form, this shape, as well as this shape. So tau is a hyperparameter. It defines well, how fast, how quickly you reduce weight with the distance from the x. Again, it introduces hyperparameter. That's the bad news. But the good news is that it fights overfitting. Now, using this approach, this regression, for this x1, you will have this line. So this line obviously doesn't fit all points, but it fits points which are close to x1 perfectly. And now you use this line, this blue line, to make the prediction for x. Weighted linear regression is what's called non-parametric machine learning algorithm. That means there are two families of algorithms basically. First one is parametric. That means that we have a fixed set of parameters, fixed set of data, of weights for the model. With non-parametric models, we don't have fixed number of data. In other words, for weighted linear regression, we have infinitely many data, because for each value of x, you will have different omegas, and training the model with those different omegas, you will have different weights. So basically, it's as this is continuous variable, you will have infinite amount of axes here possible on this axis, and correspondingly infinite number of data. So that's the first approach for changing cost function and basically improving your model with the change of cost function. Any questions about weighted linear regression? All right. If no questions, let's go further. Next. Well, you might wonder where the cost function comes from. If it's something that is given to us from someone like me, or maybe some smarter person, some just, because someone thinks that's good, if it's an empirical stuff, or if the cost function is something that comes naturally from the problem itself. For example, when we started the very first data science group here in Ukraine, very first in Ukraine, in software, it was like 3 to 4 years ago or so. The data science was a new field. We didn't have people of this profile on job market, so we were looking for enthusiasts basically and trained them later. When I interviewed people to my group, I didn't ask them a lot of math. I didn't ask them math at all, basically, except a single question, just to understand how deep they understand the machine learning, the tools itself. And my question, the most popular question I asked, the only one, it's the single question from math in all the interview. So the only question I asked was like this. That helped me understand how deeply the candidate understand the machine learning. The question was like the following. This is the cost function. Now you know it, right? It's standard thing. That's least squares. Why do we have 2 here? Any ideas?
Because the deviation can be positive and negative.
Good guess. How about now?
Because we also pay attention how far it is from the real number, not like the absolute value, but...
Why not 4, 6, 8? Why is 2?
I need to find it.
Pardon?
It's the distance between points according to the geometric theory.
Oh, well, the distance according to geometry, like Euclidean distance. Well, what does it give to us? Why Euclidean distance makes sense to us?
We need to find the derivative.
Well, we can find derivative of any power. So that doesn't. Well, that's fine. I didn't get any answers during the interview process. That's fine. I did hire people anyway. So the answer. There are different answers to these questions. The one of them I will tell you right now. So the answer comes from the nature of regression model itself, which basically which basically rely on some probabilistic assumptions about the nature of the problem. So, let's take a look at linear regression again. We have some points, right? Some training examples, and the line that should fit the point. Imagine the perfect line, that perfectly trained model, the best model that you can imagine for this problem. That would look like this one, like blue line, right? Of course, the good model that is not an overfit would have some errors for all of your training examples. You see those x's with the real value of this point and the predicted value of this point according to the model, the blue line. So we can also rewrite our model in this form. This form is basically like the following. It says that for each of the training examples, right, which is x, I, y, I, that's the training example. For each of them, we can express some true value of y, true price of the house, you can think about it this way, as the prediction that is made with this blue line, plus some error term. Error term is this dot line. It might be positive or negative, depending on which side of the line the point is. And if we rewrite hypothesis as a simple linear function, it's going to be this way. Is that clear? Do you agree with this? Good, perfect. Now, tell me, for the perfect model, which looks like this, what would you expect this epsilon to be? What would you expect this error term to be?
Minimum.
Pardon?
Variation.
The variation, what do you mean?
Statistical term variation. It should be the minimal epsilon. Could be.
Right. Pardon?
Random variables. Both.
Yes, they are random variables indeed. So it's epsilon I. That means for each of those. So if you describe them all, they indeed are random variables. What would you say about those random variables?
They sum to 0.
Yes, that's first thing, and second thing.
Mean value of is 0.
They're from normal.
Yes, they are from normal distribution, right? So we would expect those things to be to follow a to belong to some normal distribution with the mean 0. So they should sum up to 0. That's the natural thing to do, right? If we add them also, so that's going to be 0. That's why the mean here will be 0, the mean of this distribution. And they should have some standard deviation. And the overall is like this bell curve, which is now it's distribution. It's not the weight, it's normalized. So the sum under the bell curve is 1. What this tells us is that we expect to see quite a lot of small deviations from 0. So we expect to see lots of small errors, but quite few, big, large errors compared to the others, right? So, fine. Now we know that we expect this epsilon error term to come from some normal distribution. What do you know about this normal distribution? We can rewrite it as a standard thing, that's standard normal distribution, right? With the mean 0, that's why we don't have mean here, it's just 0, we just remove it out of there. Now, we can also just remember that each real price of the house is predicted price plus some error term, and we can express error term out of this expression, which now is the real price minus the prediction, right? Now we can put this thing out to here, right, to this probability distribution, and see that the probability of this y, so the probability of having this price for the house of this space, given some parameters theta, which is not a random variable, that's why it's semicolon, right? It's not the dependent variable, it's just the parameter. So it should come from this distribution. Now we just put this error term expression here, and you'll have this one. Now if we have a point, any point, say this one, we can, using this formula, we can calculate what's the probability of existence of this point if we have some specific parameter theta. So given any possible line here, this line, any other line, we can calculate for each point the probability of this price, basically. Now, but that's just a single point, right? Next, what we actually want to do from probabilistic standpoint here, and what we really do with machine learning, because we don't minimize cost function, in fact. In fact, what we do, we maximize the probability of existence for the chaining set. It might be a bit complicated, but I would maybe draw it here. Say, you have some points that look like this. And you know that the errors should be from normal distribution. If you have the model like this, right? What's the probability of existing of those points? Well, you have huge error terms here, huge here, and huge here. And they all are positive, you don't have negative terms, right? So you just calculate the probabilities of those out of Gaussian distributions of all of them, I mean separate. And you have 4 probabilities for those points, right? Good. Then, if you change the line to be this one, then you have different error terms. Like this maybe. And they are much smaller. So indeed, the probabilities that you have for the blue line will be higher compared to those that you have for the red line. Now, again, it's just for a single point. Now we would like to calculate the probability of existence of the whole data set. How would you do that? Well, the points itself are conditionally independent out of each other. That means that the fact that the 100 square meters house is priced at 100K doesn't tell you anything about the price of 200 square meters house. Well, in real life, it might not necessarily be true. There might be some conditional dependence, but we assume that they are conditionally independent, which is fine for us. And in this case, the variables, the random variables which are independent from each other, their joint probability is just the product of the probability of each of them. So the likelihood of existence of the whole training set, all points we have, is just the product of probabilities of each point, which is this one. We just put the expression from this Gaussian to this product. Is that clear? Are there any questions about that? All right, good. Now, what we're going to do now, we would like to pick values of theta which maximize this expression. So it's an optimization problem, basically. Everything else is known. We know y, so that's the real price of the houses. We know x, which is the space of the house, right? What else? We know pi, of course, and we know some. Well, we don't know it, right? But well, it doesn't affect the maximum value of theta. That means no matter what is the sigma, the theta that maximizes the expression will be the same. So you don't care about it really. Now, those how many of you are familiar with advanced optimization or optimization at all? Right. For those of you who are familiar, you can take a look at this expression and imagine how would you maximize it in this form, which is quite a complicated problem. That's why we use a trick. We don't maximize this. We use a trick with logarithm. Logarithm is the, well, basically, the idea of logarithm trick is that if the function is monotonically increasing, then the maximum of this function will be in the same point as the maximum of the original point. That means the maximum of log likelihood, I mean the parameters theta, which maximize likelihood, will be the same as parameters theta that maximize log likelihood. That's why we can use log. I can apply logarithm to this expression. Logarithm is good because it replaces product with sum. Sum is much easier and much better for optimization. Now it's just you can safely skip this complicated expression. Just take a look at the final one. You can go through it in your spare time. I do not expect you to go right now through all this expression. So it's just for your information. Don't waste your time on trying to do this one. Just try to follow the idea. So after using logarithm trick with this likelihood function, we will end up with this expression. In other words, the log likelihood of existence for all our points, is this one. It's some number of points, m, which is the number of training examples. If you have 100 houses, the m will be 100 and so on. Times log some constants minus some constant times this expression. Now, take a look at this expression. It has some negative coefficient in front of it. And we would like to maximize the existence, right? Maximize the probability of existence. So, this expression will be maximum when the second term will be minimum. This second term, minimizing the second term doesn't depend on this coefficient. And we end up with this expression. Theta, which parameters, the value of parameters theta, which maximize log likelihood, is the same value of theta which minimize this expression, which is least square. So, in other words, cost function for linear regression is not just something that is given to us. It comes just from the assumption that the error terms should come from Gaussian distribution. And you might also think about the cases when there is not. For example, imagine that you are building a model which predicts the number of users for your website or number of buyers from your store, for example. Naturally, you can't have 3.5 buyers. You have either 3 or 4 because, well, it's people right there, discrete. While Gaussian distribution is about continuous variable. So, in other words, the assumption about Gaussian distribution of the error terms will not apply to your problem anymore. And you might want to change it. You might want to say, okay, fine, now my error terms are not from Gaussian distribution, they are from Poisson distribution, which is sort of the same as Gaussian, but for discrete variables. And by applying the very same logic as we've seen just here, you can come up with different cost functions which give you better predictions. So just changing the assumption to the better one that fits your specific problem, you can increase the accuracy of your model. Just a single step, which changes everything. Any questions about this Bayesian approach to linear regression? No questions? Good. Does anyone want a break? Good. All right, let's proceed. Next, classification. As I mentioned yesterday, we have two types of regressions, which is linear regression for continuous variable and logistic regression for discrete variable. Housing prices was continuous variable because the price might be anything from 0 to, I don't know, a million or something. And it's just convenient for us to model this as a continuous variable. But you have huge class of problems which use discrete variable. For example, imagine you're working for a healthcare company and you are building as a model which identify if the tumor is malignant or benign given the size of the tumor. You now have two types of target variables of y, right? Y is no more from 0 to a million, like with housing prices. It's now either 0, which is benign maybe, or 1, which is maybe malignant, right? So as the size of the tumor increases, the probability of the tumor being malignant basically increases, which is a natural thing for us to, as we understand cancer today. Now, how would you build a model to to solve this problem, basically. The approach is pretty much the same. Well, the whole machine learning is the same. First of all, you should come up with some hypothesis. Well, we use linear function as a hypothesis. Now we know linear regression. Why not fit linear regression to it? Why not use it? Well, we can actually do that. We can try to use linear hypothesis. We have something like this. The bad news, and we can just say divide it as 0.5. We'll say that everything that is predicted as higher than 0.5 with this model is malignant. Everything that is less than 0.5 is benign, which is fine. But the drawback is that the long tails. So, for example, if you have much more of the malignant tumors here, this will shift the line towards, well, just decrease the angle, I would say, right? And decreasing the angle will move the value of 0.5 towards further towards the x-axis. Right now it's somewhere here, and using this line for classification, we will put these tumors into benign, which is incorrect. So maybe we can just come up with the better hypothesis function, right? Again, it's your decision as an engineer what hypothesis function to choose, at least so far, for 1 hour more. So you can come up with some different hypothesis function. And the standard choice for classification hypothesis function is known as logistic function or sigmoid. Sigmoid has this form, this shape. And it fits the idea of malignant and benign tumors much better than the linear function itself. Now, it has this kind of form. It's also called, it might be also expressed with logics. So, you can also find this expression for the logistic function where that is called logic, which is also minus theta transpose x. So that is basically a line, a linear thing, which is put into this expression. Next. Now we follow the same strategy. Now we have hypothesis function. With hypothesis function, we can somehow count the probability of existence of every point, right? Same thing we've done with linear regression, but now with classification. Again, this is the shape of the logistic function, which fits, which scales, which increases monotonically from 0 to 1. And it is never less than 0, never more than 1, which is a good way for us to model the probability itself with the logistic function. So we can use it to model the probability of existing of every point. So as we change theta, parameters theta, the logistic function itself moves from right to left and so on. And basically by choosing theta, we just choose the position of this logistic function. So let's model the probabilities. First of all, the probability of the tumor to be malignant, given some x in parameter theta, might be expressed as just the value of this logistic function. So if you take a look at this blue line, blue logistic function, right? Then we can say that, okay, that's fine. Let's take a look at this point. Let's calculate its value according to the logistic function, and let's take this value as the probability of this x, this point, to be malignant, which is kind of makes sense for the points of this for the tumors of this side. The probability of being malignant is quite high, right? And vice versa, as we know, the probability sums up to 1. Then the probability of the same tumor to be benign is just 1 minus the probability of being malignant. So it's like the same. It's like the same thing, but just 1 minus this this logistic function. But the bad news is that now we have two expressions for a single point. We have point x, and we have probability of this point being, this tumor being malignant, and the probability of this tumor being benign. Which is, well, it's kind of hard to work with expressions of two probabilities. Now, we would like to replace this with a single one. That's the expression just in one line. Take a look at it. Well, just for a few seconds. And notice how it is similar to the two expressions on the top. The value y, which is either malignant or benign, now might take only two possible values. It's either 0 or 1. If it is 0, then it cancels this term. Now it becomes 1, basically. And everything that remains is here. Again, if y is 0, then this power term also cancels to 1, which remains, which gives us just 1 minus hypothesis. On the other hand, if the tumor is malignant, if y is 1, then this guy cancels out, and all we have is just hypothesis x. So it's just the same thing, just in one line. Is that clear? All right, good. Next. Now this expression gives us the probability of existence of a single point. The same thing as with linear regression. Now we do the very same thing. We want to maximize the probability of existence of the whole data set. We do the same thing, independent point, just the product of probabilities of each point. We have the same problem with maximizing product, which is a hard thing to do. We use the same logarithmic trick. We apply logarithm, we transform product into sum, and have this expression as a sum. Now this is our cost function. Well, we used to call it cost function, now we know it's log probability. And with cost function we minimize this, with log probability we maximize this stuff. So we just want to maximize this. How would we do that? Well, I told you yesterday about gradient descent. There's also a gradient ascent, which works the same way, just instead of moving in the opposite of the derivative sign, we move, well, it's probably, that's descent, right? So we move in the direction which is opposite to the derivative, which is the sign of the tangent line of the derivative. Which with ascent we move in the same direction, basically. Now, in this case, we have to take a step this way and this way. And if with this sense the update rule was like the following, then with ascent the update rule will be same but with plus. So same idea, just changing the direction of the steps. Everything else remains the same. Now, we calculate gradient out of this expression and use it for making steps towards maximum of this log likelihood. When we are at the maximum, we just take the theta, the parameter theta, which maximizes this expression. And those are the theta that gives us the best accuracy of our model, which maximize existence of our data, basically. Now, with logistic function, one more good news is that it has very nice derivative that looks like this. That's very convenient for us. And I'll tell you a bit later how the idea of logistic function has changed the world of machine learning, how it gave a second life to the idea of neural network. So that's a pretty powerful idea. but it's also used just as simple logistic regression. Now, with this gradient descent rule, we calculate the gradient. Again, I don't expect you to understand all the derivation right now. Just take a look at the final one. So that's the gradient of this log-likelihood function, and we use this gradient in this gradient descent. So that's the gradient descent. You use this rule to update theta one step after another until you converge, until log likelihood. Well, you go on iterating while log likelihood changes significantly. You just put some threshold. Like if log likelihood, if at some step log likelihood is changed just slightly, then you stop iterating. You think you're on the top of that field. So you just maximize the stuff. You just train the model. So that's how it works. That's how basically everything in classification at least works, and in conventional probabilistic machine learning. You take some hypothesis to describe your model. Using this hypothesis function, you can derive the probability of existence of every point. Then you maximize the joint probability of the whole data set, and you're done. The parameters which maximize this joint probability are the parameters of your trained model. Everything else, everything that that simplifies stuff, the idea of cost function basically is simplification. This is just the top layer of all this bottom idea of how it works. Next. The next question you might have is, how would we define hypothesis? Is that something? All right, now we know that cost function is not given to us, but comes naturally from the idea, the assumptions about the problem. But what about the hypothesis? Is hypothesis function such as linear or maybe the regression, I mean the logistic function, does that come from from some respectable human being, or maybe it comes from the problem itself? In fact, it does come from the problem itself, and the thing that lies under the classification and regression is called generalized linear model. That's why we call logistic and linear both regressions, despite the fact that they solve different problems. Linear regression is about continuous variable, predicting housing prices. Logistic regression is about, discrete variables, malignant or benign tumors. But they both are regressions. Why is that? Well, because they are basically the same model. They are the same, but it comes from different assumptions. Let's take a look at them. Now it's going to be hard. So if you miss something, just go through the slides in your spare time, because that's really important. So to begin with, I have to introduce what's called exponential family model. The statement is that probability distribution belongs to exponential family if it can be represented in this form. If you can, for any probability density function, if you can represent it in this form, then it belongs to exponential family. So far so good. This exponential family expression have those parameters. Mu, which is called natural parameter, t of y, which is called sufficient statistics, and a out of mu, which is log partition function, and basically it's just the normalization coefficient. This log partition function is responsible for probabilities summing up to 1, basically. Now, what is generalized linear model? It is the way to come up with your own machine learning models, basically, that works like the following. We have 3 assumptions. First assumption is that if your target variable, first assumption is that your target variable should belong to exponential family. What is target variable? Target variable is y. For houses, it's housing prices. So if the price, what probability lies under the housing price? For the cancer detection, tumor detection, it's either it's malignant or benign. So which probability is there? So if those probabilities are out of exponential family, that's fine. First assumption is met. Second assumption is that if our goal is to predict sufficient statistics. If we would like to predict t of y, then we are good. We can use generalized linear model or GLM. Luckily, for most of the distributions out of the real world, sufficient statistic is just y. So we would like to predict expectation, mathematical expectation of sufficient statistic. In other words, we would like to predict expectation of y, which also makes sense. I'll tell you. That's important. What does it say to us? It says to us that if we have some number of houses, for example, houses of the very same size, what the model really gives us, so what it would predict, and we have some number of prices, right, for those houses. What it would predict? It would predict mathematical expectation of all of these. So it's just the expectation of yi given xi. How would it affect life around you? For example, we will have on Saturday a movie session, right? You should have noticed that in the in your calendar. It was my toy project. I used machine learning to colorize all the movie from 1939. And it works kind of well, it's fine. But what you would notice is that the obvious problem which I'm working on right now is that it's kind of often fall to sepia. You know the sepia filter for your Instagram or something. So it colorizes things kind of fine, sometimes. But often for complicated things, it just falls into sepia. So if it doesn't know how to, what color should be this specific pixel, it makes it sepia. Why is that? Well, because it predicts the mathematical expectation. It doesn't know what this pixel is really about, so it just predicts the mean of this random variable. So from all possible values for this pixel, predicts the mean. And mean for all possible colors is sepia. That's how it affects my life, at least my life in this third project. And that's how it would affect, if you understand this, right? You can type it. So if you understand why, how you end up with this sepia, you can say, okay, now I understand how it works, let's do something with it. Well, if you don't understand this, well, then you are probably done with this state. You cannot go any further. So that's just a quick note on how this idea would affect your real models. It's just predicting the expectation of your target variable. And the second one is that natural parameter nu and the inputs x are related linearly. We basically say that nu should be theta transpose x. That's the line. That's why it's called linear model. Now, let's take a look at a linear regression, logistic regression, and how they might be derived out of your generalized linear model. First, what can we say about the distribution of target variable of y for tumors? Is it malignant or benign? Well, those variables, this variable might have only two possible values. It's either 0 or 1. And we know that the distribution that satisfies this type of values, it's called Bernoulli. Bernoulli is a very simple distribution. It's just, it says that fine, you have some probability, you have two possible values, it's 0 or 1. You have some just two possible, two probabilities basically of the variable being 0 or 1. And you have a parameter phi which defines the probability of 1, and naturally the probability of 0 is 1 minus phi. So that's Bernoulli distribution. You can take a look at Wikipedia. They have pretty good explanation of all the distributions. And the Bernoulli distribution is this one. Now, the exponential family is, again, this one, is the very same as it was on the previous slide, so the same expression. Can we represent Bernoulli distribution as the exponential family? Can we change, somehow overcomplicate this expression to make it look like this? Well, we actually can. This would look like the following. We use the same trick here to express Bernoulli distribution in one line. Then we start complicating things. We start adding exponents and logarithms and stuff like that, until we come up with this expression. That looks like exponential family. Fine. Now we know that Bernoulli distribution belongs to exponential family distribution. What's next? Next, we identify the parameters out of this thing. We identify nu, which is all right. Now this is nu, right? T of y. Now this is y, and so on. We don't care about this one at all, and we often don't care about this one either. Now we can express out of this nu, we can express p, which now looks like this. And take a look at this one. Does it look familiar to you? That's the logistic function, basically. Now, we want to predict mathematical expectation of t of y, which is y. Then the model which we derive would predict the mathematical expectation of y, which is the thing that we would like to have, basically. We would like to have for each size of the tumor, we would like to have the mathematical expectation of this tumor being malignant. That's what the model would give us. That's fine also. Now, recall the third assumption, that the sufficient statistic nu is related to the input x linearly. That means we can replace nu with theta transpose x, and that's how we get the logistic function. So again, just take a look at this. We know that hypothesis should be mathematical expectation of this guy, given some parameters of the tumor and some variable theta, right? Now we know that it is basically, we go to Wikipedia, right? Take a look at the Bernoulli distribution and see what's the mathematical expectation of Bernoulli distribution, and it's going to be phi. That's also what comes from Wikipedia naturally. Now we take a look at what's phi out of our derivation from the GLM. It's this one. We replace it with this, and replace this nu with theta transpose x. That's how we come up with the hypothesis function for the specific class of a problem. Say if you work on the problem of predicting number of visitors to your store or your website, which we know is Poisson distribution, you can do the same exercise with the Poisson distribution, and that would give you a hypothesis function that would fit your problem the best way. You will basically have the best possible hypothesis function. Now you know what to do next. Now you know how to come up with the hypothesis function just knowing the distribution. Then you take this hypothesis function, you come up with the probability of existence of every point, then you maximize joint probability and take the thetas, which maximize this probability. And now you're done, the model is trained. So that's how machine learning really works. Next, let's take a look at the Gaussian distribution. Does it work with exponential family distribution? In fact, it does. But also, at least for the purpose of this lecture, I would like to use some trick. It turns out that the parameter standard deviation, it doesn't affect final theta. So we can assign any value to it, right? The thing that I mentioned earlier, no matter what is standard deviation, the theta that maximizes the overall expression will be the same. That's why we can replace it with any value we like, and we like it to be 1, because that cancels it out. We like things to be cancelled out. There's also a generalization of this approach to any value of standard deviation, and you can go through it on your own if you like. We will proceed with this approach. So, now, we cancel out standard deviation, and now we can transform Gaussian distribution to the form of exponential family, which is this one. We can also, well, we basically do the same thing. We take parameters of the exponential family distribution out of this one. Then we go to Wikipedia, to the page of Gaussian distribution, and take a look what's the mathematical expectation of Gaussian distribution is. And you'll see that it's mu. So the Wikipedia says that it's mu, and now we replace mu with nu, because that's what we got from transform the distribution. Now we replace it with nu, and we know that nu is related to the input linearly, so that's theta transpose x. that's how we come up with the hypothesis function for linear regression. So now, as you can see, linear regression and logistic regression comes up from the same family, basically the same model. And you can use this approach to build your own models out of any distribution you like. For example, one of the sort of standard questions is if we can inform logistic regression to work with some larger number of classes. For example, for tumors we have malignant and benign tumor, which is just 0 or 1, and it's Bernoulli distribution, that's fine. But for example, we could have a problem of distinguishing people, cats, and dogs, which is 3 classes, right? Can we somehow modify logistic regression to work with more classes than just 2? In fact, again, we just follow the same routine, starting with the idea that, all right, now it's not Bernoulli, now it's multinomial distribution. Multinomial distribution is very same. It's basically similar to Bernoulli, but instead of this one, now it gives you some probabilities on other values. And so on. So that's the multinomial now. You take this multinomial distribution and GLM and produce hypothesis function for it. And I will not take you through all the routine because it's really scary, but that's what you'll have in the end of the day. That's the hypothesis function for the multinomial classification model, which is called softmax regression. For those of you who are familiar with neural networks, you might have heard this before. Softmax is sort of a standard activation function for the output layer, which comes basically from the softmax regression. The idea that comes from the generalized linear model. So in machine learning, everything is pretty much connected. The state-of-the-art models of today, deep learning is inspired or affected directly by conventional machine learning, which is here. You'll have classes on deep learning later, and I really think that understanding conventional machine learning would help you a lot. Any questions about GLM? All right. If there are no questions, I think it's time for a break. You can grab a coffee and come back in. Well, help me. When should we come back? 10 minutes. Fine. Okay. 10 minutes sounds like a time.
Нет, в смысле поставил пакет, ручками посадил. Вот. Ну, смотри, его только через сокеты можно использовать? Нет, в смысле, как скрипт его через питон опять. Нет, просто я это больше разницы пробовал. Не, ну
Exponential формується дистрибуції по лінії та об'єкту.